Hello everyone, I am Dr. Sudhan Sharma from School of Computer Information Science in Indira Gandhi National Open University, and this session is actually a revision session about the important concepts which we learned in the block number 2 about Algebra 2, wherein we had explored about the units covering inequalities, quadratic equations, sequences and series, and many more concepts we had learned in this part Algebra 2. So, what are the important concepts? Are in this algebra 2, we had explored the unit number 1, which is about sequences and series. We learned about arithmetic progression, geometric progression, geometric progression, and harmonic progression also. And we had solved an ample number of numericals. And if you had gone through those numericals, gone through the session along with the self-learning material, you might got have the better understanding about the concept of the sequences and series. Subsequently, we had explored the unit number 2, which is about the complex numbers, wherein we learned about the algebra of the complex numbers, what complex numbers are. Apart from this, we also understood about how to represent the complex number in their polar form and draw the Argand diagram. We also explored about the De Moivre's theorem and how to use it in solving the problems. Thereafter, we in unit number 3 of this block, we learned about the equations, wherein we learned how to solve the quadratic equations, cubic equations, biquadratic equations. This is what we learned in unit number 3. Finally, in unit number 4, we explored the inequalities and we learned how to solve the linear inequalities and a system of inequalities. Apart from this, we also learned about how to solve the quadratic inequalities. The important parts that we learned about to how to find the nth term of an arithmetic progression, geometric progression, harmonic progression. We also learned what actually they are, arithmetic, geometric, and harmonic progression are. Also, we understood about the sum of the n terms and some of the infinite terms in different progressions. And we learned how to obtain the sum of first n natural numbers, their squares and cubes. Apart from this, the complex numbers are very important, and you are supposed to explore n number of numericals which are given in your self-learning material, and they will better explain you if you go through your self-learning material after the sessions which are already delivered. The sessions covered about the polar representation of the complex number, the algebra of the complex number, and about the De Moivre's theorem. Apart from this, we learned in the section of the complex number, which the concept of cube root of unity. This concept is very important and very frequently asked in examinations, and you are supposed to solve the problems given in the self-learning material using the properties of the cube root of the unity. Apart from this equation section, we learned how to solve the quadratic equations, cubic and biquadratic equations, and find the value of the symmetric expressions involving the roots of the cubic and quadratic equations. And apart from this, we learned when we know the roots, but we don't know anything about the equation, then how to form the equation provided the roots are available to us. And in the inequalities section, we learned how to graph the inequalities and how to find the solution set of the compound inequalities. Apart from this, we learned about the inequalities involving the absolute values. This is just to revise you about the important concepts, important formulas, and some of the numericals. Likewise, over here in the arithmetic progression is a progression wherein there is a common difference in between the terms. Likewise, we are having a progression, say a plus d, a plus 2d, a plus 3d, and so on. Then a is the first term and d is the common difference in between the subsequent terms. So, in order to find the nth term of an arithmetic progression, the general formula for is given by an is equal to a plus n minus 1 into d, where an is the nth term and simply a is the first term of the arithmetic progression, d is the common difference, and n minus 1 is about that up to nth term we want what the nth term is. So, n is the number of terms. Likewise, over here the example is, say we are given an example, an arithmetic progression a plus 2b, comma a plus b, comma a minus b, and a minus 2b. Now, following the pattern, you will find that in subsequent terms we are adding the term minus b. We are adding the term minus b. As a result of which, the common difference turns out to be minus b, and the starting term of the equation, that is first term, is a plus 2b. Now, applying the formula for the nth term, we get an is equal to a plus 2b plus n minus 1 into minus b. Solving this, we will get the answer a plus 3 minus n into b. So, this is the nth term of the arithmetic progression given to us in this example. I hope you recall that what we had done when we were discussing about arithmetic progression. Simultaneously, we had also discussed about the difference of the two terms of an arithmetic progression. Likewise, the arithmetic progression given over here is a plus d, a plus 2d, a plus 3d. Then the difference in between the two terms, that is the rth term and the th term, will be given by the difference between the rth term and the th term. That means the rth term will be a plus r minus 1 into d, and the th term will be given by a plus s minus 1 into d. So, AR minus AS is required to be calculated. So, on calculating AR minus AS, we will substitute the values or AR and AS and solve the expression. Finally, you will get the expression AR minus AS is equal to R minus S into D, which is quite important, and when we are going to solve the numericals. Now, there is a formula for the sum of the n terms, and we learned how to calculate the formula when we were delivering those sessions. The solution turns out to be the sum of n terms is S is equal to n by 2 into 2a plus n minus 1 into d. And where you can say that you can write this expression 2a plus n minus 1d as S is equal to n by 2 into a plus n minus 1 into d. So, you can say that this is, say, the last term, nth term. You can say L, this is the last term, this is the first term, and this is the first term, this is the first term, and this is the last term. This a plus n minus 1d is the last term. So, you can say Sn or S is equal to n by 2 into a plus L. So, if you know the last term of the series and you want to find the sum of the entire progression, then you can say S is equal to n by 2 into a plus L. So, this was discussed when we were discussing about the calculation for the sum of n terms. We had also discussed about the geometric progression, and we learned that the geometric progression is a type of progression wherein we are having a term called common ratio. That means the geometric each term is multiply a common factor r, and this is the progression ar square, ar cube. You are observing that every previous term is multiply the ratio r, common ratio r, and you are getting the subsequent terms. So, the nth term of the geometric progression is given by ar to the power n minus 1. We understood how to apply this expression to solve several numericals when we were delivering these sessions. Similarly, as there was the concept of the difference of the two terms, in the case of geometric progression, there is a concept of the ratio of the two terms of the geometric progression. And say an and am are the two terms in the geometric progression, then substituting their values using the formula ar to the power n minus 1 for the nth term, then we will get ar to the power n minus 1 upon ar to the power m minus 1, wherein by solving, that is a and a cancels from numerator and denominator, and rearranging the exponents, you will find it is r to the power n minus m. So, the ratio of two terms in geometric progression is an by am is equal to r to the power n minus m. Thereafter, on the same lines as we had discussed in the arithmetic progression, the sum of n terms of the geometric progression is given by the expression a r to the power n upon a into 1 minus r to the power n upon 1 minus r. And this formula of sum of n terms reduces to Sn is equal to Na if the common ratio is 1. Apart from this, there is one more observation, that if the common ratio lies in the interval minus 1 to 1, then sum of the infinite geometric progression reduces to A upon 1 minus R. So, these 3 points are quite important. Equation number 1, equation number 2, and equation number 3. These are the 3 formulas which are supposed to remember when you are going to calculate the sum of n terms of a geometric progression. Now, we had also discussed about arithmetic and geometric progression. And this is a special type of progression wherein the two progressions, that is the arithmetic progression and geometric progression, goes hand in hand. Likewise, over here the term T1 represents the first term of both arithmetic and geometric progression. Say A represents the arithmetic progression and B represents the, say, geometric progression. Then there is a common difference in the concept of arithmetic progression. There is a common concept of common ratio in the geometric progression. So the subsequent term after B will be BR as per geometric progression, and the subsequent term should be A plus D in case of the arithmetic progression. Following the same rule, the subsequent term T3 will turn out to be A plus 2D and BR square. So that means it is a composite of the two progressions, arithmetic progression and the geometric progression. The arithmetic progression follows the pattern A plus D, A plus 2D, and geometric pattern progression follows the pattern B, BR, BR square, and so on. Since two progressions goes hand in hand, so the nth term of an arithmetic geometric progression will be given by the term Tn, and which will be the composite of the nth term of the arithmetic progression and the geometric progression. This section represents the nth term of the arithmetic progression, and this section represents the nth term of the geometric progression. The product of the two is actually representing the nth term of the arithmetic geometric progression. We had gone through the sum of n terms of an arithmetic geometric progression, and this was the formula which was discussed for the sum of n terms of the arithmetic geometric progression. And we learned that when n tends to infinity, and then the sum formula of the n terms reduces to AB upon 1 minus R plus BDR upon 1 minus R whole square, where A and B are the first terms of the arithmetic and geometric progression respectively. R is the common ratio, D is the common difference for the arithmetic progression. I hope you are able to recall that how we had solved several numericals when we were exploring this concept of sum of n terms of the arithmetic and geometric progression. We learned about the harmonic progressions, and we understood that that arithmetic progression and harmonic progressions are quite closely related. The inverse values of the arithmetic progression represent the harmonic progressions. Likewise, if a sequence say A1, A2, A3 of a non-zero numbers is said to be in harmonic progression if 1 by A1 plus 1 by A2 plus 1 by A3 forms an arithmetic progression. So, the terms given in harmonic progression and arithmetic progressions are interrelated because one is inverse of other. And we can recall it with the help of an example which we had solved in our earlier session also, that find the 10th term of the harmonic progression 1 by 3 plus 1 by 7 plus 1 by 11 plus 1 by 15. Now, applying the formula for the 10th term of the AP, now considering the values given in the denominator, that is 3, 5, 3, 7, 11 and 15, they form the arithmetic progression with a common difference of D equal to 4. So, applying the formula AN is equal to A plus N minus 1 into D, you will get A10, that is the 10th term of AP, is A is equal to 3. So, N is equal to 10, N is equal to 10. And D is 4. D is given by value 4. Substituting these values in this formula, you will find that the 10th term of the harmonic progression turns out to be 1 by 39, 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 , 39 So we had explored this much in the sequence and series. Apart from this, some of first and natural numbers and their squares are expressed by these formulas. These formulas were explicitly discussed with the help of several numericals when we were going through those sessions. That means if we are having n natural numbers, say we need to sum up 1, 2, 3, 4, that is 1 plus 2 plus 3 plus 4 up to n, then the resulting sum will turn out to be 1 by 2 into n plus 1, or we can simply say n into n plus 1 by 2. Similarly, if we want to find the sum of the squares of the number, that is 1 square plus 2 square plus 3 square up to n square, then the sum will turn out to be n into n plus 1 into 2n plus 1 by 6. But apart from this, the sum of the cubes of the numbers, that is 1 cube plus 2 cube plus 3 cube and so on up to n cube, the final sum will turn out to be n square into n plus 1 square by 4. Or you can directly see that this will be square of this. You can say n into n plus 1 by 2 whole square. This turns out to be n square into n plus 1 square upon 4. So they are quite easy to remember. Now, in complex numbers, we learned what complex numbers are, and we defined that there is an entity square root of minus 1 which is repeatedly used, and in order to address a square root of minus 1, we incorporated iota as the representative of the complex number, and the complex numbers are represented by the z is equal to a plus ib, which is given over here. And the real component, there are two components, the real component and there is an imaginary component. So the real component of z is given by a and the imaginary component of z is given by value b. We learned how to explore the concept of the equality of two numbers by solving several numericals. We understood that a plus ib is a, say, complex number z1 equal to this and z2 is equal to c plus id. Then establishing the inequality means that the real components and the imaginary component should be equal. And by substituting, by making them equal, we solved some of the numericals wherein we understood by applying the concept of the equality of complex numbers, we can solve some of the equations. And the two examples were discussed in the sessions also, wherein say we are supposed to find x and y if 3x plus 4 is equal to 12 plus 8y. So 2x plus 4 iota and a plus 8y iota. So these two are the complex number. So equating the real component, that is 3x minus 12 and 4 is equal to 8y, you can calculate that x is equal to 4 and y is equal to minus 1 by 2. So this is how we understood the equality concept in the algebra of the complex number, and we had also explored about various other operations of the algebra. Uh, uh, and conjugate of the complex number is an important concept, and the conjugate of a complex number, say a is equal to ib, we learned that its conjugate z bar will be given by a minus iota b. So the sign of the imaginary section is altered, that is, it become from positive to negative or negative to positive, and we are supposed to find the conjugate of the complex number. And we also learned about how to find the modulus of a complex number. We learned that if, say, z is equal to a plus ib is a complex number, then its modulus will be given by the square of the complex value, real part and the imaginary part. That is, square root of a square plus b square will actually represent the modulus of the complex number. Likewise, over here, z is equal to 2 plus 3i is a complex number. The modulus will be given by square root of 2 square plus 3 square, that is 4 plus 9 square root of 13 will be the modulus of the complex number. We also explored various property of the modulus of the complex number in that respective session. Apart from this, we learned about how to represent the complex number in an argand plane, and we learned that the coordinate point p is equal to x I y is actually a complex number x plus I y, where y is the point lying on the y-axis and x is the point lying on the x-axis. So that means the point in the plane x plus iy represent the complex number. So likewise, we can have x plus iy lying in the first uh, coordinate plane, first quadrant, and x minus iy will be lying in the fourth quadrant, and x minus iy is actually the conjugate of the complex number expressed in the first quadrant. Similarly, we can express the complex number in other two quadrants. So the polar representation was another important topic which we had discussed when we were into the discussion of the session of the complex numbers, and we learned that e to the power iota theta is equal to cos theta plus iota sin theta is iota sin theta is the one of the important formulas, and uh, which is directly related to the polar representation of the complex number. And over here the diagram itself shows that if there is a point xy, this is a point xy, and the complex representation it is given by point p, that is x plus iy, and this line is having the magnitude which is the modulus of the complex number, that is mod z, which is nothing but equal to x square plus y square, and this line is subtending an angle theta. So this angle theta is also known as argument or amplitude of the complex number, and you can find that argument tan theta by y by x, that is theta is equal to tan inverse y by x. You can find the amplitude or the argument of the complex number, and the magnitude, or that is the modulus of the complex number, by the formula square root of x square plus y square. And this formula which we were discussing, that e to the power iota theta is equal to cos theta plus iota sin theta, is actually involved in the concept of de Moivre's theorem. And de Moivre's theorem says that cos theta plus iota sin theta to the power n is cos n theta plus iota sin n theta. This is nothing but your de Moivre's theorem. We learned about the de Moivre's theorem when we were understanding about the powers of the complex numbers. That is, when we are having, say, n complex number represented in the polar form as r1 cos theta 1 plus iota sin theta 1, z2 as r2 cos theta 2 plus iota sin theta 2, and so on. Then by performing the multiplications, we learned in the respective session that if the r part, that is the magnitude, r represents the magnitude of the complex number, if it is represented by 1, then the entire equation 1 will resolve to cos theta 1 plus iota sin theta 1 into cos theta 2 iota sin theta 2, and so on. And finally, if we substitute theta 1 is equal to theta 2 up to theta n equal to theta, then we turn out to the de Moivre's theorem, which is nothing but cos theta plus iota sin theta to the power n is equal to cos n theta plus iota sin n theta. We explored this theorem in our sessions and solved the numericals. Lastly, the cube root of the unity is one of the very important concepts, and we understood that x to the power 1 by 3 represents x cube is equal to 1, and which is actually x cube minus 1 is equal to implies x cube minus 1 cube. And we learned how to apply the cubic identity to solve this cubic equation, and we found that there are three roots: x is equal to 1, and x is equal to minus 1 plus minus square root of 1 minus 4 by 2, and we are also having the final root, that is minus 1 by 2 minus iota. These three roots are there. These three roots are actually representing the cube roots of the unity. So the cube root of the unity are expressed by the term omega, and we learned that there are three roots: 1, omega, and omega square. We also explored the value that how omega cube turns out to be 1. In quadratic equations, we learned about what quadratic equation is, and we found that ax square plus bx plus c is equal to 0 is a quadratic equation, and the coefficient of x square, that is a, it should not be equal to 0. Then the equation ax square plus bx plus c is equal to 0. If coefficient a turns out to be 0, then this equation turns out to be a linear equation, bx plus c is equal to 0. We learned about that how to find the quadratic formula and what are the nature of the solutions. And we find that if there is an equation ax square plus bx plus c is equal to 0, then we are going to have the roots of the quadratic equation as alpha and beta. Alpha is given by minus b by 2a plus square root of b square minus 4ac by 2a, or you can simply say minus b plus square root of b square minus 4ac upon 2a. The other solution will be beta is equal to minus b minus square root of b square minus 4ac upon 2a. Depending upon the discriminant which is given by this is the discriminant d is equal to b square minus 4ac, we can identify that what type of solution is if b square minus 4ac is equal to 0, that means alpha is equal to b is equal to beta, and the equation is having only one real root. But if b square minus 4ac is greater than 0, then b alpha and beta are actually two distinct real numbers and there are two roots. If b square minus 4ac is less than 0, then alpha and beta are two distinct complex numbers as the solutions and there are no real roots. So by looking at the discriminant, you can find that what type of solution is there, that whether the real roots exist or not, or the roots existing are complex or what type. We are going to have either a one real root or two real roots. So you can interpret about the type of solution. Now we also learned about that how to form the quadratic equation provided the roots are given to us. We learned that if alpha and beta are the roots of an quadratic equation, then x minus alpha and x minus beta is equal to 0 is actually the representation of the quadratic equation ax square plus bx plus c, and we can write the equation ax square plus bx plus c in an equivalent form in the form of its by using its roots as x square minus sum of roots into x plus product of roots. The product of roots is actually representing the constant term and the sum of roots is actually representing the coefficient of the term x. And the sum of roots is given by the expression minus b by a, and the product of roots is given by the expression c by a, where a, b, c are the coefficients of the respective terms of the quadratic equation ax square plus bx plus c equal to 0. So b is the coefficient of x, c is the constant term, and a is the coefficient of x square. So you can go that if the quadratic equation is known to you, you can find the roots, and if the quadratic equation is not given to you, only roots are given to you, then you can form the quadratic equation also. We also learned about the biquadratic equation, the triquadratic cubic equation, and the biquadratic equation. The cubic equations are the equations of the representation a naught x cube plus a1 x square plus a2x plus a3 equal to 0, where a naught is not equal to 0, that is a naught is the coefficient of x cube. If a naught turns out to be 0, then the equation will be resolved into a quadratic equation. On the same line, the biquadratic equation is a naught x to the power 4 plus a1 x cube plus a2 x square plus a3x plus a4 equal to 0. On the same line, a naught is not supposed to be 0, because if it turns out to be 0, then the equation will be resolved to a cubic equation. We learned that what is the relation between the roots and the coefficients of the cubic equations, and these three expressions are representing the relation between the roots and the coefficients of the cubic equations. Thereafter, we also learned about the relation between the roots and coefficients of the biquadratic equation, and these are the expressions which are actually representing the relation between the roots and the coefficients of the biquadratic equation. We also explored inequalities, wherein we learned that in real life we are continuously facing about the concept of inequalities, but that means the equations, rather we should say inequations, having the connecting symbol in between the left hand side and right hand side could be greater than, less than, greater than equal to, or less than equal to. We learned about the statement, the equivalent statements for the symbols, that means how to express the mathematical expressions into the English sentences. And we learned how to solve the system of linear inequalities. We find that we understood the concept of the absolute values, that is the absolute value of x is such that it is equivalent to x if x is greater than or equal to 0 and minus x if x is less than 0. So absolute value of x is the maximum of minus x and x. We also learned how to graph the linear inequalities in two variables, wherein we understood how to represent the boundary region, be it represented by a solid line or by a dotted line. Apart from this, how to draw the boundary line by finding the intercepts and connecting the intercepts, how to find the region, that which region satisfies the inequalities and two variables. And we also learned about the quadratic inequalities, how to solve the quadratic inequalities, and with the help of respective numericals in the respective session. And I hope by going through these this representation which is given in this session, you are able to revise at what are the important concepts delivered till now in the block number 2. Now we are into the situation wherein we are supposed to extend our discussion to our block 3. In the subsequent session, we are going to discuss block 3, which is about the calculus, and wherein we are going to discuss about the differential calculus, integral calculus, application of the differential calculus and integral calculus. Thank you very much, and I again advise you to go through the self-learning material, solve ample number of numericals so as to have the better understanding of all the concepts delivered in the sessions. Thank you very much.